Hello everyone. Today I will be explaining you about fixed bias. So moving on further about fixed bias, first let me give you a brief introduction of transistor and its biasing techniques. So just going back into the history, John Bardeen, Walter Bratton and William Shockley invented the first working transistor at the Bell Labs in 1947. So this is a model of a transistor, how it looks. So a transistor is also known as a BJT, that is a bipolar junction transistor. It is a semiconductor device. It is a sandwich of one type of semiconductor layer between the other type of the semiconductor layers. So each type of layer is being capable of carrying some amount of current. Here we can just notice that there are two different types of transistors here and here. This they represent the NPN and the PNP. This is the symbolic representation of a transistor. If the arrow mark is coming outwards near the emitter terminal, then it is the NPN transistor, whereas if it is going inwards, then it is the PNP transistor. Here we have the collector, base, and the emitter. There are three terminals for any transistor, and they are collector, base, and the emitter terminals. So the junction has also been named after the terminals itself. The junction between the collector and the base is known as the base collector junction, and the junction between the base and the emitter is known as the base emitter junction. The same follows in PNP also. So these are the two different types of transistors, PNP and NPN. Let's move forward. Let's talk about what is biasing. So transistor biasing is the process of setting a transistor DC operating voltage or current conditions to the correct level so that any AC input signal can be amplified correctly by the transistor. It is very important to properly bias so that it operates correctly. So, as we all know that the transistor is a device that regulates the current and the voltage flow. Okay, so it will act as a switch and amplifier accordingly to the biasing also. The way it is being used in any circuit, it acts as a switch or an amplifier. Here, in any applications of transistors, it's important that the transistor is biased properly in a correct way, which is required for that particular application. So, biasing becomes a very important technique and a very important tool to be done. And we will have three main types of biasing techniques, that is the fixed bias, collector to base bias, voltage divider bias. These are the three main types of biasing techniques. There are many more biasing techniques also, but these three are the main types. Okay, so let's go about the fixed bias. Fixed bias. Fixed bias is also known as the base bias. It is the simplest DC bias configuration. Okay, so here is the circuit which shows the fixed bias configuration. Here the VCC is being connected, but it is the biasing potential. It is not the potential difference. Rather, it is the potential at a point. Here RV and RC are the resistors. RV is the base resistor connected to the base terminal. RC is the collector resistor connected to the collector terminal. In series, they are being connected to the base and the collector respectively. And we have the emitter terminal also. Emitter terminal is grounded, and we have the IB, that is the base current, which is represented as IB, and here we have the collector current, that is the represented as IC, And VCE is the potential difference between the terminals of collector and the emitter. Then same follows for VBE also, the potential difference between the base and the emitter region. Let's move forward. Yes, in the next coming picture, I have just modified the circuit into a little more easier, simpler circuit, so that when we do the calculations, it becomes easy for us. Like when we do the calculations, we apply KVL and KCL. So that time it will be easy for us to analyze the voltage drops and the currents. So here we have taken the VCC. Here the corner points is also when we have connected VCC here, this corner points is also VCC. This corner points is again connected to the emitter region. Here the emitter terminal. So emitter terminal will be acting like a negative and this will be acting like a positive. I will just give you a brief idea here. Let's check it out later. Okay, so here I have taken it as plus VCC. Okay, and just like this. Okay, and like this. This I have taken negative to the emitter. The same follows here also. You will get a brief idea about that in the next slide. Okay, yes. As you can see here, we have taken the corner points as plus VCC, and the negative terminal is taken from the emitter because it is grounded. So it is negative here. Here also plus and here also it is negative. Okay, that is how it is plus VCC and here plus VCC. And this is kind of represented as a battery. It will become simpler when we apply the KVL in this loop and in this loop. Let's apply KVL first in this loop. Yes. So from KVL here we can see that VCC minus IBRB minus VBE is equal to 0. This is the KVL equation. So when we just rearrange it and we get the value of IB. So IB is equal to VCC minus VBE divided by RB. Similarly, let's apply KVL to this equation or this loop also. Here we get VCC minus ICRC minus VCE is equal to 0. And then again we rearrange it, we get VCC is equal to ICRC plus VCE. Okay, as we know, IC is equal to beta DC times IB. So now we will substitute IB from here, from this equation. So when we substitute IB here, beta times beta is a factor, as we all know. This is the normal equation. IC is equal to beta times VCC minus VBE divided by RB. Sorry. Okay. So we can also note that VCE is equal to VC minus VE. Here VE is equal to 0 because when we connect it to the when we connect it to the ground potential is always taken as 0. The same applies for VBE also. So VCE is equal to VC, VBE is equal to VB. Here also VE is being taken as 0. So this is the main formulas which we have to learn, so that we can solve n number of problems. IB is very important, IC also, and VCC formula. When we apply the KVL equation, we can easily find these values for these formulas and all. And here VBE is taken as a standard value, as already everybody knows. I'll be just writing here. It is zero point 0.7 for silicon. Okay. and it is zero point 0.3 for germanium. This is the standard values for VBE in any transistor. If it's a silicon base, then it is zero point 0.7. If it is germanium base, it is zero point 0.3. So these values can be substituted here in place of VBE. We can get it. Okay. Let's just move forward. To get a very better picture of these equations, let's just solve one problem. We will get a nice idea. Yes, here, as we can see, this is the fixed bias example. Here, they have given us the RB value, the RC value, and the VCC value. So for IB, from the previous slide where we saw the formula, we can just write it as VCC minus VBE divided by RB. So here we have taken zero point 0.7 for VBE. Like if it's not mentioned for if either it's germanium or silicon, we can take it as silicon itself because it's the most widely used transistors, silicon based. So we can just write it as zero point 0.7 here. And substituting these values, you get this 36.8 microamperes, correct. Same for IC. HFE is given as 100. It is somewhat similar to beta factor. So we take this as beta and then beta times IB. We get 3.68 milliamps. VCE also we have to find it out. VCC, this is VCC. One second. Yes. So this is the VCC minus ICRC. 18 is given as VCC and this is. So we get 9.9 volts. This is a very simple calculation for fixed bias configuration. Just having the brief idea of the formulas or applying KVL, we can just find it out. So let's move on forward. Let's just go through the merits of the fixed bias. So it is a very simple circuit, as everybody knows, and the shifting the operating point anywhere in the region by merely changing the base resistor RB. So it is very simple to shift the operating point anywhere in the active region by merely changing the base resistor RB. A very small number of components are required, as we saw the circuit configuration itself. Very little number of components were required. So the merits are being listed down. Let's see what are the demerits also. So this is the operating point here. This operating point can be shifted anywhere in the active region with merely changing the value of the base resistor. That is why it is very simple. This is a very simple circuit. Yes. As we saw the merits, it also has the demerits. The collector current does not remain constant with variation in temperature or power supply voltage. Therefore, the pre-operating point is unstable. Very important, and it should be noted that the operating point is unstable due to the variation in the temperature or the power supply voltage. The operating point will be unstable. Changes in supply will change base current and thus cause emitter current to change. This in turn will alter the gain of the stage. So changes in the supply will also cause the base current to change and the emitter current also to change. So then this will alter the gain. This is also very important to be noted. When the transistor is replaced with another one, considerable change in the value of beta can be expected. Due to this change, the operating point will shift. So, as a whole, the operating point is unstable, and the gain of the stage also will be altered by minute changes also. Hence, we cannot be able to use in large applications. But still, we do have some usage of the fixed bias configuration. Let's see through that. Yes, due to the above inherent drawbacks, fixed bias is rarely used in linear circuits, that is, those who use the transistor as a current source mode. But it is often used in circuits where the transistor used as a switch. Where we use transistor as a switch, it is being used, fixed bias configuration is being used. So as a whole, fixed bias, it's a very simple circuit. The configuration and the circuit diagram is also very simple. It has a very few components to be used, but the demerits which listed is the operating point will be unstable and the gain also will be altered. So thank you everyone. This is all about today about fixed bias configuration. Thank you and have a nice day.